Imagine giving an AI a mouse and keyboard and turning it loose on software built before modern integrations existed. Today's computer use agents can do exactly that, accessing legacy enterprise workflows exactly the way a human employee would. Take a typical state compliance portal. For years, a housing finance team used a basic automated script to log in and check loan statuses 200 times a day. But in 2024, the portal shipped a minor redesign. The underlying code changed, and the old script crashed on the very first page. It simply halted. To solve this, the team deployed a modern computer use agent. Unlike the rigid script, this AI visually parsed the screen, read the dropdowns, and pulled the statuses flawlessly. It executed tens of thousands of lookups with 0 errors for 6 straight weeks. Then, a new state law triggered a surprise. A full-screen legal modal popped up on the portal, demanding users recertify their authorization, ending with a primary button reading "Certify and Submit." A human would have stopped to read it. The AI, specifically built to navigate unfamiliar screens, simply identified the most obvious way forward and clicked the button. The company legally attested to details nobody had reviewed. The old brittle script failed closed. It didn't recognize the screen, so it stopped. The keepable AI agent failed open. It improvised to keep moving, keeping the dashboard metrics entirely green while silently causing a major compliance incident. We rely on explicit contracts for machine-to-machine communication, but a human interface offers no contract. It responds to visual clicks and keystrokes. It is a glass wall. Making an AI act safely on the other side of that wall requires a highly specialized architectural harness. The first hurdle in building that harness is translation. You have to give the model a reliable way to parse a visual interface into structured data it can actually understand. One approach is feeding the model raw screenshots. The AI scans the pixels to find its target, but this creates blind spots. A screenshot might capture a page before it fully loads, or the model might get confused by 2 visually identical buttons because it lacks the underlying context to tell them apart. The alternative is reading the underlying code, the accessibility tree, or the DOM. This explicitly tells the agent what a button does. But custom elements, iframes, and dynamic content often don't expose that semantic data, leaving large voids the agent simply cannot see. To solve this, engineering teams use a hybrid architecture. The accessibility tree maps out the semantic structure, telling the agent what to click, while the screenshot provides visual confirmation of what actually rendered on screen. Even with both navigation methods, we hit the grounding problem. When a system calls an API, it gets a definitive status code back. Success or failure is an absolute certainty. A computer use agent has to guess. It takes a screenshot after acting and tries to infer if it worked based entirely on subtle visual changes. Relying on the AI's best guess is exactly what leads to silent failures. Engineers must build strict action verification checkpoints into the system. The agent has to be forced to locate precise visual evidence, like a specific confirmation number, before it is allowed to move to the next task. Once the agent knows how to click, we have to consider where it operates. Traditional integrations are stateless. They make one request and disconnect. A web browser session is persistent by design. If you leave a highly capable AI logged into an unconstrained session, it carries authenticated access from one task into the next. An agent asked to process a single invoice could wander into adjacent HR or finance portals simply because the links are visible on the dashboard. To contain that blast radius, you need a rigid sandbox architecture. Every run must start in a fresh, ephemeral session. The agent receives a temporary credential scoped strictly to the current task, and its movement is locked to a hard-coded allowed URLs. That isolation protects the network, but the interface itself holds unique threats. Malicious text hidden on a web page can act as a visual prompt injection, instructing the AI to ignore its original task. Or an attacker might use clickjacking techniques, styling a dangerous button to look exactly like the agent's actual target. Defending against visual attacks requires strict instruction hierarchies. The system prompt must explicitly tell the agent to treat on-screen text as data, not as new orders. And before interacting with any sensitive element, the agent must pass a verification prompt to confirm the target matches exactly what it expects. Securing these workflows is no longer about training a smarter AI model. It is entirely about engineering unyielding boundaries around what the AI is physically permitted to touch. If building this harness sounds difficult, it is, and it reveals an important truth about enterprise deployment strategy. Just because an AI agent can navigate a human interface doesn't mean it should be your first choice. This chart shows the integration hierarchy for automated workflows. At the wide, stable base is level 1, your standard APIs. Above that is level 2, extracting structured data directly from code exports. At the very narrow, unstable peak is level 3, computer use. Automating through the user interface is a high-risk last resort. Right now, the AI tooling market is rapidly merging language models directly into browser software. But none of these out-of-the-box tools ship with production-grade action verification built in. Skipping the effort of building a proper API integration to rely on a visual agent might seem like a shortcut, but you're simply trading a known development cost for an unknown and potentially catastrophic risk surface. Before a team lets an agent loose on a production system, they must draft a rigid verification specification. First, map out every irreversible action in the workflow. Identify the one-way doors, like financial commits, mass data deletions, and regulatory submissions, where an undo button does not exist. Next, build safety checks around those specific actions. Write a pre-action prompt that forces the agent to verify exactly what it is about to click, followed by a post-action condition requiring it to observe clear visual evidence of success. If it fails to see that evidence, it must fail loudly and stop. Finally, lock down the session limits. Strict URL boundaries and maximum action limits must be hard-coded directly at the infrastructure level. They cannot be gentle suggestions left inside a text prompt. Handing an AI agent a mouse and a keyboard opens up incredible access, but the screen itself offers no built-in safety net. To automate predictably, you have to artificially impose the rigorous rules of a contract over the chaotic reality of a human interface.